Okay, so where we left off was talking about the universal law of gravitation, which is Fg is equal to gm1 m2 over r squared, where g is the universal constant, the same everywhere in the universe. M1 and M2 are the masses of the two objects, and r is the distance from the center of one to the center of the other. If we were talking about two people, probably wouldn't matter if you measured from the outside edge of their body to the outside edge or center to center. But if we're talking about the Earth, it's going to make a big difference if you're measuring from the outside edge or the center. So we always say center to center. So in the last video, we found the gravitational force of attraction between two objects of mass 80 kilograms and 60 kilograms. And we discovered it was really, really tiny. So then we found the gravitational force of attraction between the Earth and one of those objects. We kept the 80 kilogram object, and we found that that was significantly bigger. So what if we wanted to do it for the 60 kilogram one? As long as you're at or near the surface of the Earth, the radius of the Earth, then the r isn't going to change. It's just going to be the radius of the Earth. So the only thing that will change, well, this 80 would switch to 60. Or if the object was 200 kilograms, it would switch to 200. Okay? So think back to Newton's time. There weren't calculators. So people got a little frustrated with having to keep multiplying these big numbers in. And they eventually said, well, since if we're at or near the surface of the Earth, these numbers don't change. The only thing that changes is this m. Couldn't we fill these in as a constant? So if you take your calculator and you do 6.673 times 10 to the negative 11 times 5.98 to the 24th divided by the 6.38 times 10 to the 6 squared, you can find the constant that they replace these with. This works out to be 9.803, not quite 9.81. And that's because the mass of the Earth would be rounded and the radius is rounded. So this is roughly equal to 9.81 meters per second squared, which we call little g. At or near the surface of the Earth, it's 9.81 meters per second squared. The further we go from the Earth, the bigger this r gets, the smaller this value gets. If we go to a different planet, then the mass and the r will change. Those planets will still have a little g. It just won't be 9.81. This little g is called the acceleration due to gravity, which is what we called it when you were in grade 11. But it has another name that I may have said in grade 11. I'm not 100% sure. It's also called the gravitational field strength. So the size of little g tells us how strong the field is. Closer you are to the object, the stronger the field. Further you are away, the weaker the field. What's it really equal to? So if we go back and we think about our equation Fg equals gm1 m2 over r squared, well, what we have circled here then is really gm over r squared. So little g is equal to gm over r squared. Or if you look at this equation, Fg is equal to mg. Right? That's what we used all through grade 11, which means little g is also equal to Fg over g. So if you take this gmm over r squared and put it in there, over m. If you take this gmm over r squared and put it in where Fg is, one of the m's cancel, and you end up getting this. So these are the two equations to find the acceleration due to gravity, which is really called the gravitational field strength. I'm just going to flip over here. Okay, so our equations then, Fg equals g m1 m2 over r squared is the gravitational force. Little g is equal to Fg over m, and little g is equal to g m over r squared. Okay, this m is the mass creating the field. Right? If we look back at the other page, we can see that it's like the mass of the Earth. Right? It's the one that didn't I can't get the page turned over, but honest it was. Right? It was this 5.98. Whereas this M is the 80 kilograms. It's the object being brought into the field. Object brought into field. Okay. But wait, this was supposed to be a preview of electrostatics. Why have I been talking about gravitation? Gravitational force and field. Well, because electrostatics parallels this. Think about the fact that we just said there's a force between any and every two objects that have a mass. Well, there's also a force between any and every two objects that have a charge. Think about the fact that we said any object that has a mass has an area around itself, and if another object enters that area, it's going to experience a force. Well, the same is true for charge. All charges have an area around themselves that if another charged particle enters that area, it's going to experience a force, right? If this is a positive charge and I bring another positive charge near it, it's going to experience a force. Now, in physics, charge is Q. Don't ask me why, but it is. And so our electrostatics equation parallels our gravity. Instead of Fg, it's going to be Fq. There's a constant, we call it K. Then it's Q1, Q2 over R squared. So it looks exactly like the gravitational equation. A constant, the two charges instead of the two masses, and then the distance from the center of one to the center of the other. In charge is measured in the unit Coulomb. Okay, named after a dude, and it's a capital C. K, this guy was Newton's Universal Law of Gravitation. This one is Coulomb's law. Okay, K then is the electrostatic constant. And it's an easy one to remember. It's 9 times 10 to the 9th Newton meters squared per Coulomb squared. That's what we use in physics. Really, it's 8.988 times 10 to the 9th Newton meters squared per Coulomb squared. So in Science 12.2, depending on what we're finding, sometimes we'll use the more exact version. Okay, so this is the force acting between two charges. There's also an electric field around that charge, and we can find it exactly the same way that we found the field for gravity. There are two equations for field. Electric field is a capital E. One way of getting it is like what we did here, taking the electrostatic force and dividing it by the object being brought into the field. So this is charge entering field. The other way is then if you put KQQ over R squared in here, one of the Q's will cancel and you'll be left with KQ over R squared, where this is the charge creating the field. So the equations exactly parallel each other, and that's why I started with gravity, right? The fields are a little bit different. For gravity, there's only one way that gravity acts. It's always going to pull you down towards the center of the earth. But in electrostatics, it's not always going to be a force of attraction. If the two charges have the same nature, then they're going to repel each other. Whereas if they have opposite natures, then they will attract. Okay, but that's something for another day. That'll be the next day I see you. We'll start from here. Okay?